In the last several classes, we have been discussing about transmission lines, and we have discussed how the voltage and current exist on the transmission line and give rise to several other effects, including the wave phenomena, how waves move from left to the right and also right to the left. We also discussed several consequences of those wave phenomena, that is impedance transformation and standing waves, to name a few. But if you recall, we had started the discussion on transmission lines in the very first lecture of this course with the intention of seeing how electromagnetic waves behave. Now, while discussion of transmission lines, we did not use the term electromagnetic waves, but we implicitly understood that the transverse nature of the waves that are in the transmission line are some manifestation of electromagnetic waves. So we had discussed transmission lines with the intention of converting a 3D problem into something similar to a 1D, which makes the analysis little more simple and easy to understand. Now, having come across or having understood how the transmission line works, it is now time for us to make the big jump into 3D. But what you need to understand is that 3D space and variation of different quantities in 3D is often not very easy to visualize. So what we are going to do is that we are going to form the knowledge of transmission lines that we have gained so far, wherever required, as a basis for our discussions. Now, one of the immediate motivations to study 3D is that it has immediate applications like transmission of wireless signals. When we talk of 3D space, there are many applications. For example, transmission of wireless mobile signals. For example, when you pick up your mobile phone and make a call to your friend, from your phone to the base station or the nearest mobile tower, the communication between your phone and the mobile tower is purely wireless. So essentially a wave, or waves rather, flow back and forth between your phone and the base station. Second, the second example is satellites. When, for example, if one of our satellites is orbiting around the Earth, we can talk to the satellite from the ground station. So again, that communication is wireless. Now, the immediate difference what we can see between transmission line versus 3D space is that there is no concept of a boundary in a 3D space. That means when I am making a call from my mobile phone, the wave does not see any boundaries. Whereas transmission line was a bound structure. Bounded structures. What it means, we had a pair of conductors where charges would flow in the conductors, giving rise to the currents and hence the wave phenomena. So I am not saying that when wireless signals travel, it is always unbounded. What I am saying is that when a wave leaves our mobile, just like transmission line, it does not know what is at the end of that line. So it may happen that the path that the wave has to travel from your phone to the nearest mobile tower need not be an obstacle free path. There could be some metallic objects, there could be some non-metallic objects in the way. For example, buildings, lampposts, and the wave may have to encounter those. So then how do those obstructions or obstacles impact the wave? Now, the first difference what we saw was bounded versus unbounded. This second difference between wave in a transmission line versus wave in 3D space, the immediate and most obvious difference is that in transmission line we have the concept of voltage and current. In 3D space, in air for example, we cannot talk of voltage and current because there are no conductors to carry the charges from one point to other point. So but 3D space has no conductors to carry the charges. So now the question is, just like in transmission line, how we were able to connect a source at one end, giving rise to oscillating charges and therefore obtaining oscillating behavior of voltage and current waves. How do we make the energy flow in 3D space? Now, first question is it possible? Well, it is possible because we just saw two examples. We have a number of wireless communications which do happen. So then in that case, how are we able to sustain waves without conductors in 3D space? Now, one thing is obvious is that in 3D space there can be No voltage and current, absolutely. No voltage and current, so to speak. So, to understand how the waves travel in space, you need to look into a little more fundamental property of the waves. So, electromagnetic waves, as we have discussed, is nothing but waves comprising of electric and magnetic fields. Now, this is very important. Electric fields and magnetic fields can give rise to an electromagnetic wave. But does it mean that if I am able to generate an electric field and I am able to generate a magnetic field, I will have electromagnetic wave? Not necessarily. The electric and magnetic field must obey some certain cardinal rules for them to coexist and thereby obey the wave phenomena. And that is something which we are going to slowly but surely see as we progress in the course. So, one more thing is, unlike voltage and current, many of these quantities, for example, electric field and magnetic field, these are vector quantities. V and I are not vectors. They are scalars. So, as you know, vector quantities are those which have a magnitude as well as a sense of direction. For scalar quantities, there is no such thing. So, for example, if you go back to your physics, examples of scalars include temperature profile. In terms of electrical quantities, you can have electric potential, and vectors. The easiest examples are electric and magnetic fields. So, something tells us that many of the quantities which we are going to see in 3D space, some of them will be vectors. So, therefore, it is very important for us to be able to differentiate what is scalar, what is vector, and what are their properties. So, one thing that we know about electric and magnetic fields is what causes them. Now, since we are trying to establish the foundations for electromagnetic waves, we need to understand the nuances. That is, what are the fundamental quantities that give rise to electric and magnetic fields. For example, if I have a charge, a single charge somewhere in space. Now, this gives rise to an electric field. So, what is electric field? Electric field around the charge or because of the charge is an indication of the force that this charge will exhibit on any other charge that is in the vicinity. So that is what is called as electric field. So how much force it is able to exert on other charges in its vicinity. So electric field indicates essentially that. So now what gives rise to magnetic field? If I have one charge, or if I have a few number of charges and I am able to make them move. Suppose I have this conductor. Remember, the conductor is not 3D space. The space around the conductor is 3D. Suppose I have some charges inside the conductor and I am making them move. What is happening then? Then I can say that some kind of current has been set up inside the conductor. What is causing the current is a later part. There would be some voltage source or something of that kind. So we know that whenever current starts flowing, a magnetic field is created around it. So this was found after experiments by many physicists. So most notably by Ampere and Oersted, and many of the electric field experiments were done by people like Coulomb, Gauss and more. So we know that a stationary charge gives rise to an electric field, while moving charges give rise to magnetic fields. So that is the very basic idea behind how the field components at least are existing. So now suppose I have a scalar function. Since we are going to be talking of vectors, scalars, as far as fields are concerned, it is very important to brush up the basics of vector calculus and its implications before we delve into anything serious. Now let us say, for example, there can be many scalar functions. For example, temperature, electric potential, the distribution of charges along a surface. Let's take temperature for an example. Let us say that temperature, that is T, it is a function of 3D space, x, y and z. So think of it this way. I am looking at the temperature distribution on the Earth's surface as well as the atmosphere. That I can think of as a 3D function. So for that, I just need to know the temperature at the point. The direction of temperature is not very important because temperature does not have a direction. So it's like saying, if I have a Cartesian plane, 3D plane, three axes x, y and z. Now let me name the axis. Which should be x, which should be y, which should be z. Let us say this is x. Then I will make this as y. Then this will be z. So as you know, there is something called a unit vector along x, y and z. So they must follow this property. the cross product or the vector product of the x and y must be equal to the unit vector along the z-axis. So if you notice, these two are orthogonal to each other and the product is also orthogonal. Now looking at the direction, if I now take my right hand and curl my fingers from x to y, indicating x cross y, then the direction of my thumb gives me the direction of z. Similarly, z cross x will be equal to y. So again, if you apply the right hand thumb rule and you curl from z to x, you will see y as the product, so on and so forth. So you cannot say x, y and z. No, that is not correct. This right hand thumb rule and the vector multiplication should follow. So I can have temperature at different points, x1, y1, z1. At some other point it could be x2, y2, z2. Some other point over here which could be x3, y3, z3. So at different points the temperature may also vary as a function of x, y and z. So the easiest example being, if I am standing on the surface of the earth and I am moving horizontally on the surface along the same latitude, then I can definitely say that if I am moving along the same latitude, the temperature variation may not be very high. So now if I am still on the earth's surface and I start moving northwards, I can say yes, there will be some appreciable change in the temperature may drop. Now, if I start from the Earth's atmosphere and I start moving towards the atmosphere vertically upwards, away from the Earth's surface, so over there I can say that definitely the temperature variation will be much higher. Moving from a south latitude into a north latitude on the Earth's surface, there may be some temperature change. If I travel 1,000 kilometers, maybe the temperature may drop by 2 or 3 degrees as I move northwards on the Earth's surface. But if I go 1,000 kilometers vertically up from the Earth's surface, then there is going to be a very big difference in temperature. It's going to be probably, at least 50 to 100 degrees drop, depending on how far we go. So the way the temperature changes as we move in different directions is very important. So what we can say is that the change in temperature is direction dependent. We just took an example to prove that. So even though I know that this temperature function is a scalar, but the change in temperature as a function of 3D space is a vector. So now there exists a function which helps us find in what manner the scalar quantity changes in different directions, and that is called as the gradient function. The symbol for that is an inverted delta, or the Greek symbol nabla, or what we call as del. So this del is defined as an operator using partial derivatives in the 3-axis and the unit vectors along the 3-axis. So the unit vector along the x-axis is x cap, and the partial derivative of the function is nothing but this plus the derivative along the y-axis plus the derivative along the z-axis. So I can say the gradient of T, or the temperature, is nothing but this. So what you can see, the gradient of temperature is now a vector. So if we are able to capture our temperature profile properly using the xyz coordinates or axis as a scalar function, then the vector function delta t or del of t, the gradient of t, will give us the manner in which the temperature is varying. So this is also called as a directional derivative. So we saw how this del operation can be used on scalars to get the directional derivative. Now, how can the del operation be used on vectors? We have a vector f. So as you know, we represent vectors using a vector notation. Let us say on the Cartesian plane, it has 3 components: fx, fy, and fz. So we have this gradient operation which we had defined like this. So if we were now to apply this vector operation on another vector, we can have 2 options. We can either do a dot product or we can do a cross product, because they are vector quantities. And if you now apply this in the multiplication form, you can have 2 forms of multiplication of vectors. One is the dot product, the other is the cross product. So now let us see the vector product. Let us first see the dot product. So I can write del dot f, the dot product of these 2. So dot product is very easy to calculate. You just have to multiply the corresponding terms. So in this case, it will become the individual derivatives of x, y, and z terms and the sum. So this will be nothing but del fx by del x plus del fy by del y plus del fz by del z. So what you can see is that when we are doing the dot product, the unit vectors essentially get multiplied and become a scalar. So this entire sum is a scalar quantity. As you very well know, the dot product of two vectors is always a scalar. And this scalar is nothing but the sum of the partial derivatives of the x, y and z components. So this quantity is not just some kind of a mathematical arbitrary quantity. There is a name for this. This quantity is called divergence. This quantity is called divergence. So, divergence means divergence is an indication of the flowing nature of the vector or vector fields. Now let us say, for example, I have a charge, some q, and I am defining a closed surface around this charge. So now I can define any point on the surface, let us say P. The electric field might look like this. So the divergence at point P is nothing but the flow indication of this vector per unit volume. Why I am saying volume is because this is a closed 3D surface. So if I now look at this part of the surface, I can see that waves are going to come out like this. Not the waves, sorry, the field is going to come out like this, the vectors. So if I now zoom in onto P, I will see at this surface definitely the vector is going to behave like this. This is called as a vector field. So what I am seeing is if I am observing from outside the surface, it appears as if the vector field is originating from a point and is diverging, because the field lines are essentially moving away from each other. So now if I were to define this electric field as the quantity F, the vector field F, in this case, if I were to take the divergence delta of F at point P, you will definitely see that this is more than 0. Now this indicates that the vector is flowing outside and is diverging. Now, if I were to do something opposite, if I took that surface and I saw that the field lines are essentially going in, so these are an example of convergent fields. So if I were to now take the divergence in this area, del dot F, you will definitely get it less than 0. It means inward flow and convergent field. That means definitely they may likely meet at some point. When can del dot F be 0. This will be 0 when the vector field is neither converging nor diverging. So for example, if I have a surface and the vector field looks like this, the lines are all parallel to each other. In that case, the divergence will be 0 because they are neither converging nor diverging. So in terms of liquids or fluids, divergence is also used as a measure to see whether those liquids or fluids are compressible or not, whether they are expanding or compressing. So this is what is there about divergence. Now, if I take the cross product of del and f, so that is nothing but del cross f. And how do I define it? Using my vector notation. It is something of this kind. I have the unit vector over here, then the partial derivative operations, and the three components of f in the form of a determinant. So this can be opened up in this form, x hat followed by this determinant, minus y cap, so on. So this is the way you can open up a determinant. So what we see is that the cross product of del and f is also a vector, as it very well should be, because we know that the cross product of two vectors also gives us a vector. So now there is a name for this quantity. It is called the curl, C-U-R-L, curl. Now what this curl indicates is the rotational nature of the vector field. If the curl of a vector is non-zero, that means it has some rotary components. Let us take an example. Let us take an example which you may have already studied. Suppose I have a circular disc. I have a circular disc and this disc is rotating counterclockwise along this line of symmetry or this axis. So I can define, if I am standing over here at the edge of the disc, I can say that the velocity at this point is v. But I can also define the angular velocity omega. And if the radius of this disk is some radius r, which is also a vector, I can define v is nothing but omega cross r. Now the question is, can I represent omega in terms of r and v? Can I represent omega in terms of r and v? I can. I leave it to you as an exercise to prove that And if I were to now express omega, that would be nothing but half of del cross V. So this is nothing but the curl, and what I am seeing on the left is giving me the rotational information of the vector field. So as long as this is rotating, this omega can never ever be 0, because the curl, which is indicative of the rotary nature of the vector, can never be 0. So if del cross any f is not equal to 0, it means f is a rotational vector. If the curl of f is 0, that means f is irrotational. One more example to think of for the curl is when there is a cyclone. When there is a cyclone, essentially the storm moves like this. The velocity vector of the storm essentially goes like this. It may rotate clockwise or anti-clockwise. So if you were to measure this velocity vector and take out its curl at the time of the cyclone, well, don't do that, but if you were to do that, you would see that the curl of this velocity vector would never be 0 because it is rotating. Compared to that, if I have a vector field which is like this, for example, the wind velocity on a normal day, this vector is moving linearly, so you will see that the curl of this vector could be 0 because there is no rotational component absolutely. So different vector fields, different properties. So the physical implication of divergence and curl should be clear, because these will have direct applications when we are discussing about electric and magnetic fields. Now, when we are talking of vectors or vector fields, there are certain laws which have been defined, or theorems I should say. So the first theorem which is important to know is what is called as the divergence theorem. So the divergence theorem comes as a consequence of the law of conservation of matter. So suppose I have some kind of a 3D region which contains some fluid. I have a 3D region which contains some fluid, and the fluid velocity is given by this vector v, small v. Then the divergence theorem states that the total expansion or the compression of a fluid inside the 3D region equals the flow of the fluid whether outward or inward. So, let me repeat this. The divergence theorem states that the total expansion or compression of the fluid inside this 3D region equals the total flow or the flux of the fluid inward or outward. So if the liquid is compression, that means there is inward flow. Suppose there is a 3D surface which I am taking this way, and there is some fluid. So if the fluid is compressing, definitely the flow will be inside. If the fluid is expanding, then the velocity vector field will definitely look like this. This is called as inward flow and this is outward flow. So how can I define what is the net flow? The net flow, which can be inward or outward. Now when I am talking of flow, I have to look at only the surface. I will not care about what is inside the surface. I will just have to see how much of the fluid is coming out or entering the surface. So therefore, I have to take the velocity vector and integrate it over the area. So essentially what will happen? It will be a double integral over the area of the surface of the velocity vector v dA, where dA is nothing but the area differential. So which is nothing but, if on this surface it is the actual area multiplied by the normal vector. The perpendicular vector on the area surface. So the actual area value times the normal vector, that is the dA vector. This is the net flow. Now one part, so when we had stated the divergence theorem, we said that this net flow is nothing but an indication of the total expansion or compression. So when I am saying expanding or compressing, there is some change in volume. And expansion or compression is nothing but whether the vector field or the fluid is diverging outward or inward. So therefore, when I am talking of the expansion or compression, I will talk of a volume integral. This is over the whole volume. So the divergence of the velocity vector, which is the triple integral over the unit volume surface, unit volume element, these two have to be equal, because this is the flow and this indicates net expansion or compression. The divergence theorem was proposed by none other than Gauss. So the scientist Gauss was the same person who has given this divergence theorem. Now what you will observe, if you think a little bit more, is that the divergence theorem can be used to explain what is Gauss's law in electrostatics also. Think about this. When I am talking of the net flow or the flux, it is nothing but the electric field lines which are either coming out of the surface or entering the surface. Whereas the net expansion or compression is nothing but the amount of charge what is inside the surface. So Gauss had first proved this, and then he had proceeded to explain his law about electric fields. So this is a general case. The divergence theorem can be used to explain the Gauss's law in electric field also. Now, the second theorem is called Stokes theorem. So Stokes theorem essentially indicates the circulation of a vector. It gives you the idea of the rotational nature of the vector using the curl, but in words it states the following. It states the amount of quote unquote circulation in the vector in the boundary of a region is nothing but the circulation in the closed area. So it says circulation of a vector in a boundary is equal to the circulation of the vector inside the enclosed area. So now if I have a vector field F, suppose I am looking at, this is the boundary, and there is some vector field F over here. If I want to know the circulation of the vector in the boundary, what I will essentially do is I will start from here. I will keep integrating along the surface until I cover the closed surface. I start from here, move clockwise and come back to the starting point. So therefore I will define a closed contour integral of f dot dl, where dl is nothing but the unit length vector, or not the unit length vector, it is the differential length vector. Now inside the surface, how do I define circulation? It is nothing but the curl. So I will again take an area integral. I will take curl of f dot dA, where again dA is the area differential and these two must be equal. This indicates the circulation of a vector along the boundary, and this indicates the circulation of the vector inside this area or the surface. So Stokes theorem is very similar to what you may have understood in your vector calculus course on what we call as the Green's theorem. So Stokes theorem and Green's theorem are very similar. Rather, we can say Green's theorem is a special case of the Stokes theorem. Now, since the curl of the vector indicates its rotational nature, immediately in terms of electric or magnetic fields, I think of magnetic fields which are generated around a current carrying conductor. So the question is, can we apply Stokes theorem over here? Think a little bit. I can say that yes, along this surface I can apply the curl of the magnetic field, and at the same time the magnetic field can be integrated along this line. What should be a closed surface or the closed contour. So this is how we can say that the circulation of the net magnetic field is nothing but the integral of the magnetic field along the line. So now with this we have established some basic vector calculus, which I am sure you are already aware of from your previous mathematics courses. But we saw that these vector operations, these vector calculus operations, they don't just have a mathematical consequence, but they have a physical consequence also in terms of different quantities. So now let us discuss about electric fields. Let us say I have a charge Q placed in some medium, and I have another charge which is small q placed in the same medium. The medium has a permittivity epsilon. So then I can define something called the electric field intensity or the vector E. So if I am connecting or representing this distance between the two as some r, and I define a radial vector r along the axis connecting these two charges, then electric field intensity is nothing but, so if I say the electric field intensity due to Q, that means what is the field along this charge Q? As I mentioned this briefly earlier, that it is an indication of the force that is experienced by any other charge in the vicinity. So this is nothing but the net electrostatic force per unit charge, which we want to see as experiencing the force caused by Q. So therefore this comes out to be Q divided by 4 pi epsilon r square and along the radial vector r. So what is epsilon? Epsilon indicates the permittivity of the medium where the charges are there. But how do we define permittivity? Permittivity is the measure of the resistance offered by a medium to the formation of electric fields inside it. So you can see more the permittivity, less will be E. Less will be the magnitude of E. So more is the permittivity, I can say more is the resistance in the field or in the medium against formation of electric fields. So in some sense, permittivity indicates the measure of the resistance offered by the medium to the formation of electric fields in that medium. So in general, this can be expressed as epsilon r times epsilon 0, where epsilon 0 is the absolute permittivity of free space and epsilon r is the relative permittivity of the medium with respect to the free space. So the unit of epsilon is what? It is farad per meter. The farad is the same unit for capacitor. So this also, you know, epsilon 0 is for free space. That is something like 8.852 into 10 raised to something farad per meter. The value is not important, you can look it up in anywhere. This can also be written as 1 by 36 pi into 10 raised to something farad per meter. Some people find this 1 by 36 pi easier to remember. So what we can see immediately is that the electric field intensity depends on the charge. So more the charge, more will be the electric field. The more you move away from the charge, less will be the electric field, because then the value of R will increase. And most importantly, the electric field depends on the medium parameter epsilon, which is nothing but the permittivity. So we define one more quantity which is called as the electric displacement density, or the vector D, which indicates something very similar to electric field but irrespective of the medium. Electric displacement density is indicative of the electric field strength but irrespective of the medium. So it is defined in this form: epsilon times E. So therefore, if you apply the expression for E, you will get nothing but Q by 4 pi R square R. So this quantity is medium independent. And often this is very, very useful, because it now tells you nothing but the effect of the charge at a distance R. So now I can define something called as electric potential. Suppose I have some charge Q which has some electric field in its vicinity. Now inside this electric field, if I am moving a unit charge from one point to other point, then in some sense I am doing work against this electric field. So the work done by somebody else to move a unit charge from one point to other point, let us say A to B, that is called as potential. So if the electric field because of Q is E, and I am defining a small length element dl, which is again a vector, the electric potential V is nothing but the integral of the dot product of the two. Because as you know, the work done in general definition of physics is nothing but the force times the displacement, and that is a scalar. That is why we are taking the dot product. dl indicates the displacement and E indicates the force. So since this is not exactly work but is indicative of work, this is what we see. So now we have this negative sign because we are doing work against an already existing field, that is E. So now this V is a function of x, y and z, and it is a scalar. We had defined this, we had mentioned this briefly while discussing about scalars and vectors, that potential is nothing but a scalar. So if I don't have this integral, if I only want to consider what is the small amount of work done to move the charge along the distance dl, then in that case dv is nothing but E times dl. I can, since my potential is a function of x, y and z, I can also define my dv as a partial derivative with respect to x, y and z, and then adding them up with the length differentials, or adding them up by multiplying with the length differentials. So therefore I can say that for the x component of dv, it is nothing but del v by del x. But then this does not remain potential anymore. It becomes the potential per unit length. So therefore I need to multiply this with the length element dx. So I can do for the remaining two axes also. Now what I can do is, I am seeing that there are these three partial derivatives as well as these this small differentials or the length differentials. So therefore I can say the dv, which I wrote in this form, which is nothing but del v by del x times dx plus del v by del y times dy plus del v by del z times dz. So I can express this as a dot product of two vectors. How? I can say this times I can very easily say this. So this vector I can write it as nothing but dl bar, dl, because this dl will be a function of dx, dy and dz, but dl is indicating the small length along which we are moving from point A to B. What about this? Does this look familiar? Yes, it is. It is nothing but the gradient of V, the scalar quantity V. So therefore this is nothing but del V times dl, and as we had already said, dv must be equal to minus E times dl. So just by comparing the two vectors, I can say that the electric field is nothing but the minus gradient of the electric potential. This is a very important result. Now, let us define something called as current density. Or what we call as the conduction current density. Now, in general, if I have a conductor whose shape is some arbitrary shape, then inside the conductor if charges are flowing, since the structure is not very well defined, it is often much more useful to define the current in terms of current density. So the conduction current density, which we call as J, that is a vector, that is nothing but the current flow per unit area. So if I have some kind of a conductor this way and charges are sort of flowing or whatever, so then I can take a small area element dA bar, which is perpendicular to the surface, and whatever is the current density through this surface gives me an indication of current. So therefore I can say through this entire area the current is nothing but the area integral of the conduction current density integrated over the area element. So now, if you consider a conductor, if you consider any conductor through which current is flowing, some current I, and some voltage exists V, then using Ohm's law I can say V equals IR, where R is the resistance of this material. Now if the length of this conductor is L, this also becomes nothing but, let us say, the magnitude of the voltage is nothing but E times L. Here the potential itself is doing the work of transferring the charges from one end to other end, so therefore there is no minus sign. So IR is nothing but E times L. So current I can write, if the area is A, the cross-sectional area of this conductor is A, then current can be written as J times A, and resistance can be written as the resistivity rho of L divided by A. So A and A will get cut. Now I can define something called as conductivity sigma, which is nothing but 1 by rho, where rho is the resistivity of the material. So this is nothing but J by sigma times L, and that is nothing but EL, which is over here. So L and L get cancelled, and what we have at the end is something like this. So if you're writing in the vector form, this is what we get. So this is nothing but another way to represent Ohm's law, but using electric field and the conduction current density. So we have moved from voltage and current into electric field and conduction current density. So we had mentioned that where some unbounded medium is concerned, voltage and current become rather tricky things to work with. So therefore it is easier to work with fields and current densities. Now, suppose I have a conductor. I have a conductor and some current is flowing through this conductor. Let's say some finite current I is flowing, where I is nothing but J times A, where A is the area, cross-sectional area. Now suppose this finite current is flowing through this conductor and this conductor is very, very good. So that means for good conductor, the conductivity must tend to infinity. So therefore, if current is finite, area is finite, even J has to be finite. So if J is finite and conductivity tends to infinity, then I can say the electric field inside this conductor is almost zero. So we shall come across this electric field being zero inside conductors later on also, but this is one of the best proofs that at least in a current carrying conductor, the net electric field inside the conductor is almost zero. So today we discussed the basics of vectors, took a recap of vector calculus and saw some theorems related to vectors, and thereafter we started the discussion on electric field and electric currents. So in the next class we shall continue this discussion, which is very important to establish for understanding of electromagnetic waves and how the electric and magnetic fields are interrelated. This we shall understand in the next few classes. Thank you.